Hello!
And welcome to Hurstmoor Zoo Observatory in East Sussex with its collection of impressive and elegant domes. They still have working telescopes here and enjoy wonderful dark skies, so I'm told, when it's clear.
Well, we hope to enjoy those dark skies a little later with the Wealden Astronomical Society. But until then, we're going to talk about the lives and dramatic deaths of stars.
And the team are here too, having a tug of war. We'll find out why later. Hurstmoor Zoo was built after the Second World War and became a royal observatory in 1958. Many of the telescopes came from Greenwich, where the London light pollution had become too much. Sir Patrick Moore was a regular visitor and supporter of the observatory, using the telescopes to look at the moon. Here he is in 1984.
Of course, there are some features of the observatory which everybody knows. There is, for example, the time department. And here, the atomic clocks are now better timekeepers than the Earth itself. And it's also from here that the 6 pips come out. Then there are the telescopes at Hurstmoor, sir, which is another reason for our being here.
In its heyday, 200 astronomers worked here, and they looked at galaxies, nebula, and even comets. But the majority of their work was with the stars. They mapped the stars in the sky, measured their distances, brightness, and studied the light to see what the stars are made of. Stars make up a family, and like any family, the members are different. Some stars are big,
Some small
some bright,
and some dim.
but they're all essentially the same. They're vast balls of gas, mostly hydrogen. But the best star to look at is our own, the Sun.
And that's because the core of the Sun, we know that the temperatures and the pressures are almost unimaginably vast. That means the atoms there are moving incredibly quickly.
And when they collide, they can fuse together. And as a consequence of the most famous equation, E equals mc squared, matter is turned into light.
And that happens at a furious rate. In fact, the Sun is losing nearly 4 million tonnes of matter each and every second. So that's 4 million tonnes gone.
And another 4 million tonnes gone. And that's happening all the time in every one of the hundreds of billions of stars in our own galaxy.
In fact, as stars go, the Sun's not much to write home about. It's rather Mr. Average. And so it's time we met the rest of the family. There are hundreds of billions of stars in our own galaxy, but even from a good dark spot, you'll have to content yourself with seeing just a few thousand of them. Even the largest telescopes won't show a star as anything other than a point of light, but we do see colour. Some stars are yellow, like our own Sun, some red, and some blue. And it turns out that colour's important because it tells us how hot the stars are. Lucy and I have come to a telescope that's spent many a night staring at the stars.
Fantastic. So here we have the 1896 26-inch Thomson refractor.
Beautiful, isn't it? It's always good to see a proper refractor in a giant dome. This is what observatories are supposed to look like.
And they used to do measurements of star positions from here.
And not just positions, this telescope was used to measure the distances to the stars.
But you know, that's not the most interesting thing about this telescope. It does something really special. Let me show you. Come round here.
Okay, I'm slightly nervous when you start running for switches.
Hold on to your hats.
Okay.
Here we go. So we do not have to move the telescope, we go to the telescope.
This is the civilised way to get to your observing position. Move the entire floor. This is fabulous.
But you need to watch out for your head, Chris.
Right, thank you.
I've been told it stops automatically. I'm just going to keep pressing until it does.
Are you sure this stops?
I'm willing. Yes, there we go.
Perfect.
So what a civilised way to get up to do
It's
the
great,
observatory.
isn't it? And now here we are, we can go and look at the sky.
Yeah, fantastic.
Over 100 years ago, astronomers were trying to make sense of the assortment of stars in the night sky. Two men, American Henry Russell and Dane Arne Hertzsprung, realised that the key was showing how the brightness of a star is related to its colour. So all we've got here are the two things we know about stars. We've got their colour, but colour means temperature. So the red stars are the coolest, and the blue-white ones are the hottest. It's the opposite way around from bathroom taps. Red is cool, blue is hot.
And the other piece of information is how bright the star is. So faint ones go down here and bright ones go up here. So now all we need is to put some stars on our board, and in fact we've got some in our pocket. And the first one that we can put on is the most familiar star, the Sun. And it turns out the Sun goes bang in the middle of our diagram here. Surface temperature of about 6,000 Kelvin, so halfway along here, and then medium brightness as well. We can also do the brightest star in the sky, and that's Sirius. And Sirius is a bit hotter and a bit brighter than our Sun, so that goes up here.
The nearest star system to our own is made up of Alpha Centauri, a bit hotter, a bit brighter than the Sun. But it has a companion, Alpha Centauri b, which is a bit fainter. Put it down there. And then the nearest star to the Sun, Proxima, red, much smaller, much fainter, so that goes down there.
Now I want to extend it up here a little bit, so I'm going to put on Spica, which is a staggering 12,000 times as bright as our Sun, but because it's over 200 light years away, it's a little bit fainter how we see it, but it is bright in reality, and it goes up here.
And lots of our familiar bright stars in the night sky go here, so Vega sits about there as well. And then if we add a few more stars, we begin to see that they fill in the gaps.
And actually what's really clear is that all the stars lie along one line in our diagram, and that tells us something really important. They're all fusing hydrogen to helium in their cores. That's what's powering them. It's what we astronomers call the main sequence. But not all stars sit here. There are hot, bright stars called blue giants, like Deneb. And then there are the red giants, like Arcturus, which our Sun will become in its old age. These fuse helium at their core, causing them to swell to enormous proportions.
It's hard to get your head round the sizes of the stars, but luckily I've got an onion, and I want you to imagine that this onion is the size of the Sun as it is today.
But the Sun won't stay that size forever. When it turns into a red giant 4,500 million years from now, it will swell up from the size of the onion to be the size of the dome, and that will encompass the Earth's orbit.
And if that's not impressive enough, Betelgeuse, one of the biggest of the stars, is so large, 10 times larger in fact, that Jupiter's orbit would fit inside it. Stars don't collapse because of pressure from the core pushing up against gravity. As the star grows old, these two forces strain against each other, rather like a tug of war.
And you join us here for our stellar tug of war. We have two teams, Team Gravity, an ever-present force, trying to pull everything inwards. And then there is Team Star, which has energy and pressure on its side, resisting the pull of gravity. Team Star is nuclear. They are burning hydrogen, and you can feel the heat. Team Gravity, though, they never give up. They are a force to be reckoned with. We stand a better chance of survival if we work together. Team Star, quite magnificent, producing just enough heat and light to balance gravity. Absolute stalemate here. But Team Star running out of steam. The hydrogen has all but gone here. They are beginning to collapse. Team Gravity sensing success here, surely. But hang on a minute. Deep in the core, things are heating up here. Team Star are fighting right back. Suddenly they're right back in it, burning helium. A surge in the energy. Team Star is now a red giant, and the crowd love it. Gravity on the run here, you would have to say, Derek. But hold on a minute. Team Star has spent their fuel. They have burned up. They're all gone. Nothing left. And gravity continues pulling in. And the star collapses. It becomes a quite spectacular nebula with a tiny white dwarf at its heart. Gravity wins the day. Remarkable.
Eventually, the outer layers of the Sun will be expelled into space, becoming a planetary nebula. The core, called a white dwarf, will be all that remains of our once mighty star. We see lots of planetary nebulae in our night sky. They are beautiful and ephemeral, the death of a star caught in time.
The most massive stars, like hot blue Deneb, don't die quietly. Once their fuel is consumed, the star collapses, and the result is one of the most violent explosions in the universe. We call it a supernova. These cataclysmic stellar deaths can outshine an entire galaxy. And in 1987, we were treated to one in a galaxy on our cosmic doorstep, in the nearby Large Magellanic Cloud. The object, called supernova 1987A, has been studied in great detail ever since, and astronomers have watched the glowing rings of material spreading out into the cosmos. You can see the remnants of supernovae in the night sky, with even a moderately sized telescope. Nearly 1,000 years ago, a blue giant star exploded in the constellation of Taurus, and we see it today as the Crab Nebula. The astronomers at Hersman Zoo studied these objects and many more, and John's been finding out what it was like to work here.
Life for an astronomer at Hersman Zoo was busy, observing by night and day. With all the telescopes working at night time in the Sussex countryside, it must have been an active and exciting place to be. But there was time for some R&R, with some interesting accommodation next door. Not every astronomer gets the chance to sleep in a 15th century castle. The observatories were purpose-built to fit in with the castle setting. A flint napper was brought out of retirement to finish the outsides, and the copper domes finished in verdigris. But unfortunately, all the effort building this magnificent facility couldn't improve the British weather. Almost as soon as it was finished, plans were afoot to move to the Canary Islands, where the seeing was better, and by 1990, the observatory closed. Dr. Graham Appleby was a solar observer here. So Graham, you worked here from 1970 to 1990, really the heyday of Hersman Zoo as a royal observatory. What are some of your most memorable observations and studies that would have happened during that time?
I began observing the sun. My first job was looking at the sunspots and through hydrogen alpha filters and flares. It was a very active time in the sun. So it was amazing to actually see from the ground these sunspots erupting. And then I got involved in observing the moon, the passage of the moon across in front of stars. So looking at that was very exciting as well.
And as observatories go, it's a very beautiful place here, wonderfully
Yes.
landscaped and so on. But
Yes.
some of the astronomers in the early days that this was crafted were a little sceptical about that. You don't need a pond when you're studying the stars at night.
You can imagine this completely dark, some little lights maybe glowing, but you come out of this dome here, which I worked in quite a lot. Dome D has a 10-centimetre refractor. We used to use it to observe minor planets. And you can imagine coming out of the steps there, and if you make a wrong turn, you're in the pond. So it's not the best design. It looks great, but it's not the best design for a dark observatory.
But now Hersman Zoo is this wonderful visitor centre and scientific centre and great place for astronomy outreach. Lots of people being inspired as they visit here. So it's sort of a new kind of heyday, isn't it now?
Yes, to see these older telescopes now being used for education is a perfect link, actually. It's a perfect result.
Patrick himself was a great, great fan of this place. I'm sure he'd be delighted to see it as this great centre of outreach for astronomy, sparking new interests in astronomy all the time as people visit. The observatory here shone brightly, but all too briefly. Chris North and I are going to see how they used to study the light from the stars.
Well, here, John, we've got the largest telescope on the site, a 36-inch Yap reflector. It's built in the 1930s and moved here in the 50s, and it's quite a remarkable feat of engineering, isn't it?
It is wonderfully imposing to see it, really arresting as you walk in. And this, of course, adapted for spectroscopy, so it can decode and specifically study starlight and really tell us about the signature of stars and show us their uniqueness.
So you can do this with a prism and split the sun's light, or you can even create the same effect using the back of a CD.
Exactly.
But to see the light from other stars, which are so much fainter than the sun, you've actually got to use a telescope like this to collect enough light, because they're so much fainter than the sun. And when we do that, we see something quite remarkable in the spectrum.
I imagine this would collect rather a lot of light.
Yes.
And it would give us the chance that we can study
Indeed,
over
yeah.
here. Ah,
There was one of these on Mr. Dwyer's laboratory wall at school. Yeah. I mean, they're very decorative, but what do they tell us? This is the sun, right?
So this is a representation of the light from the sun split out into its rainbow, its spectrum of colours. And it goes from red through purple, as you might expect. But there are specific colours that appear much darker, and that's because those very specific colours, like this one here, are absorbed by specific types of elements in the sun's atmosphere. So this one in the red end of the spectrum is absorbed by hydrogen in the sun's atmosphere. And there are other elements as well. So hydrogen absorbs at this wavelength and other wavelengths as well. But we can also see that there's small amounts of calcium in the sun's atmosphere and the small amounts of iron in the sun's atmosphere. We can start to get a spectral fingerprint of what the sun is made of.
And the chart above, now this is from a blue giant star. Some of the lines are in a similar position, but there's a lot that's different about it. What differences are we seeing there?
So the first thing about the blue giant star is that it's very bright in the blue and it's very dim in the red. And that's because the star is much hotter. The fact that the star's a lot hotter also means that some of those elements in the atmosphere are completely stripped of their electrons already. Now that means that they can't absorb any light. So we don't see absorption lines, as these are called, from iron and from calcium and that kind of thing. We mainly just see hydrogen in the atmospheres of those stars. So we had the diagram, the Hertzsprung-Russell diagram that Chris and Lucy were showing us earlier. And we had the sun right in the middle, and the hot blue stars up in the top left. And then down the bottom right, we had the cold red stars. And this is one of those cooler red stars. We can see it's very bright in the red. It's much fainter in the blue. That tells us it's much cooler. But also, the spectrum's a lot busier. There's an awful lot more lines in there. And whereas the atmospheres of these stars, these warmer stars, are dominated just by atoms in their atmospheres, in cooler stars, you can have molecules, you can have chemistry. This is atoms joined together. Molecules absorb light at many, many more colours than just the pure atoms do it. And if you go to even colder temperatures too, things get even more complex, because not only do you get redder and redder until you're almost invisible to the light we see with our eyes, not only do you have molecules and you have chemistry in the atmosphere, you get something you really wouldn't expect. You get weather.
You certainly don't associate that taking place on a star. And this takes us to that strange world of the brown dwarf. Very curious object, sort of like a duck-billed platypus in a way. Hard to classify exactly what they are.
Brown dwarfs are a new addition to our star chart and are the coolest and dimmest of stars. Hertzsprung and Russell could only have dreamed of these strange beasts. Part of the difficulty has been seeing them because they don't shine brightly like our star. To find them, we need infrared telescopes, which can pick out cool objects. Ben Birmingham from the University of Hertfordshire is a brown dwarf hunter. He uses telescopes like Spitzer and WISE to look for these elusive beasts of the star family, which lurk in the cold, dark parts of space.
They're very peculiar objects. I'm sort of struggling to conceptualise where they sit. They seem a bit like sort of the missing link in between stars and planets somehow.
They certainly are the missing link between stars and planets. The warmer ones look a lot like stars. They show a lot of the behaviour we see stars having. But then the lowest mass ones look like planets. They have weather, for example. You see dust cloud weather and things at sort of about 1,000 degrees centigrade. So you go from studying the kind of the plasma physics of charged particles in a stellar atmosphere with protons and electrons flying around to atmospheric chemistry, where you're using the language of planetary science rather than stellar physics.
And what kind of temperatures are we talking about here?
Well, they range from the temperatures of the coolest stars at about 1,700 degrees centigrade to much, much lower temperatures. In fact, a few years ago, I was very pleased when I pushed the record, along with a team of astronomers at Hertfordshire, down to about 500 Kelvin, which we thought was about good for oven chips.
Yeah, congratulations on that record.
Well, yeah, it's been taken pretty comprehensively now. And the WISE mission, a satellite from NASA, has managed to push the temperature limit down to about 300 Kelvin, which is room temperature.
So hang on, room temperature, like this temperature?
A bit warmer than this temperature, I think. but yeah, about 300 Kelvin, 20 degrees centigrade.
So how do you say whether something is a star or whether something is a planet?
Well, that's tricky. So people tend to take a kind of gut feeling approach. Does the thing taste like a planet? Does it smell like a planet? The definition officially is when something's low enough mass that it doesn't burn something called deuterium in the core when it's
like
very
heavy
young.
hydrogen.
Heavy hydrogen, yeah. Whether it burns that in the core when it's very young, then we call it a planet if it's orbiting a star. They have atmospheres that are predominantly composed of hydrogen, but the molecules we see in the atmospheres are things like water, methane, and at the coldest temperatures, ammonia. And it's probable that when we get to these temperatures, we'll start to see water clouds in their atmospheres.
Where are the nearest brown dwarfs? How close are they to us?
Well, they're very close. In fact, just recently, an American astronomer working on his own, looking through the WISE data set, found a brown dwarf within 6 light years of Earth, which makes it one of the closest objects to the Sun.
What, the third closest stellar system? Something like that? And we had no idea it was there?
No idea at all. It was hiding against the very crowded background of the galactic plane. Lots of people have been looking, but it's a very hard job to find these things. And a lot of people were kicking themselves.
Yeah, it seems slightly careless to have missed a star-like object that close.
Careless is a strong word.
All right, sorry, I don't mean to be rude. Just, I guess it tells us how little we know about the galaxy.
Yeah.
So is that the closest one?
That's very hard to say. Probably not. I would say if we're still finding things at 6 light years, there may be things even closer. It would be pretty ambitious to say that's definitely the closest one.
The other odd thing about these stars is that they don't seem to die. They just get colder and colder. They are immortal stars, ending their lives in the lonely emptiness of space. We're hoping to see some brighter stars tonight. Wealden Astronomical Society is resident here, and they've joined us to keep us company. Paul is talking to John Pilbeam about some objects we hope to see later.
What sort of area of amateur astronomy is your particular thing? What grabs you?
Star clusters and double stars. I love double stars, yeah.
I don't very often hear people say that, actually. It's sort of like the really geeky aspect of amateur astronomy.
Yeah.
What's your favourite double star, then?
Alberia.
I think you're going
I'm going to have to say that.
It is quite nice.
Andromeda, I think, has got a nice second one to that with the coloured stars, but certainly Alberia is the favourite.
Those lovely orange and blue, it really is.
It's the blue that catches you.
Gary Palmer likes studying my favourite star, our Sun. Pete's finding out why he enjoys solar observing so much.
It's a perfect thing, of course, for the public because it's during the day.
That's right.
Yeah.
It's also nicer for me because I keep warmer. So.
No, I've seen some of your pictures and they are spectacular.
Thank you.
You specialise particularly in what's known as hydrogen alpha imaging, which is taking pictures of the sun's chromosphere, the prominences and whatever's going on like that. You've been looking at the sun today, haven't you?
Yeah, it's been really interesting today. There's some nice detail on there. Have been fighting with the wind and the clouds a little bit today.
It's been a bit windy here, yeah.
But did manage to get some nice images.
Right, anything particularly stand out?
There was a nice flare that came off the edge of the sun earlier on and gradually developed into a nice loop prominence.
Oh, really?
Yeah,
they're
that was
fantastic,
really nice.
aren't they?
Yeah, it was lovely to watch. And there was a lovely large prominence coming off that had some fantastic shapes in there. And also a lot of sunspots. So it seems like there's a lot of activity starting again over there.
Do you think the sun's starting to wake up a bit?
I think so. I think,
About time,
yeah,
isn't it?
it's very, very late. I think it's a little bit like our summer this year.
So, Paul and Pete, what of the stars in the June sky at the moment? We're just waiting for the clouds to cooperate with us. Looks like more are blowing in.
Doesn't look promising, does it?
Not at the moment. But at least, though, June is the time for the noctilucent clouds.
Ah, yes, that's
now, we
right.
like those.
Well,
We
Pete's
do.
obsessed with them.
Well, actually, they're great because the nights in June are really, really short. So these are things that are easy to see if they're there. They glow with an electric blue light, like a network of clouds in the night sky. They're really high-altitude clouds. They're picking up the light reflecting off them from the sun, which is below the horizon. And they're something which are unique to the summertime.
They do have that wonderful ethereal glow to them.
They do, and the interesting is how subtly they can change over the course of 10-15 minutes. They really are dynamic objects, lovely things.
And June also the time of the moon's perigee, the supermoon as they call it.
That's right. This is This is one of those events that it normally gets people very excited, doesn't it? The moon is going to be a tiny fraction of a bit larger in the sky.
This is actually on the 23rd of June, and
Yeah.
it's because the moon is at the closest point in its orbit,
Perigee.
and that coincides with it being full moon this time. It has the name of supermoon. That's actually an astrological term.
Oh, we
It
won't
was
have
an
such things
astrologer that
here.
brought that in.
Don't mention them again.
Let's call it a perigee moon.
Well, spectacular as that moon will be, hopefully it won't wash the stars out too much. So which particular one should we be looking out for in
Well,
June?
we've got the lives and deaths of stars, something that we've been looking at on the programme. We've got those in the summer night sky. So let's start with star clusters, and the wild duck cluster, M11's a good one, isn't it?
That's lovely, actually. Yeah, that's at the bottom of Aquila the Eagle. There's a little curve of stars that points to it. And when you look at it through a telescope, even a small telescope will show a beautiful smattering of stars there. They're supposed to be arranged in a sort of V shape, which is supposed to look like a cluster of wild ducks flying across the sky.
It does actually look a bit like what it's supposed to. It's one of those rare objects that is.
You've
what
got a
it's
good
supposed to be.
imagination there, because I've never seen that.
That's a viewer's imagination. But we also have a nice globular cluster. It's low down in the constellation of Sagittarius, and this is in your teapot asterism, isn't it?
That's right. It's at the heart of Sagittarius, which sort of marks the region where the centre of the Milky Way is. It looks exactly like a teapot.
Not exactly like
Oh, it does. It's exactly like a teapot. But if you imagine where the steam would be rising out of the spout of the teapot, there's loads of stuff around there. You've got the Lagoon Nebula, which is one of only 2 areas of nebulosity you can see with the naked eye in the night sky. You've got the Trifid Nebula, which is a beautiful thing to look at through a telescope. 3 dark lanes, cuts it into 3. And then you've also got M22, which is the brightest globular cluster, which could be seen from the northern hemisphere. And you've got M25, which is another beautiful
Deep
cluster.
sky treasure trove.
It
Isn't
is,
it?
absolutely,
It really is.
yeah.
It's a pity it's so low down. That's the only unfortunate thing about it. Well, at the other end of the spectrum, we have star death, and this is represented by a fine selection of planetary nebula. In particular, I think the Ring Nebula in Lyra is a really fine example of this. And I think you should try this from London, John. I think that telescope of yours would pick it up.
And if you've got a large enough power, conditions are good, you see a sort of ghostly smoke ring in the sky.
Well, there's a fine thing to look out for. June, full of promise.
And hopefully some clear skies.
Yes.
Many fine objects to observe in June, so long as the weather cooperates. And you can use Pete's sky charts to help locate them, including the teapot and its steam, if you like. Just go to our website at bbc.co.uk/sky at night.
We have had no luck with the weather, and it's even starting to rain. Weald and Astronomical Society are packing up. Let's hope next time we can come and enjoy Hurstmont Zoo's dark skies. In the meantime, it's just the ducks and us that are left behind to enjoy this beautiful and atmospheric observatory.
We've had a great time here at Hurstmont Zoo. It's been wonderful to see these lovely old telescopes.
When we come back next month, we'll be celebrating the summer solstice by launching our More Moon Marathon.
We've selected some easy to find features on the moon for you to tick off during those warm summer nights.
And so, until next month,
Good night.
Comedy coming up here on BBC4 next this evening. We're heading out to dinner with the Likely Lads in just a moment, and then causing a disturbance at the post office as the Banbury Intricate Craft Circle gets going. Our brand new series Up the Women continues at 8:30. Stay with us.